But I was saying that it's better if you speak, because now I don't see the Zoom panel, so I don't know if someone has asked questions in the chat. So feel free to interrupt me anytime, whenever you like.
Okay, should I introduce Alessandro?
Yeah.
Okay, well, Ale, there is a bit of echo, I think.
Okay, you see.
So, well, just well.
Still?
No. Well, anyway, so we are having Alessandro Fortuna today. It's a great pleasure. So he did his master in Padua and Milan, so in Italy. And then for his PhD, he moved to the Netherlands, where he worked with Rudy Wijnands and Michiel van der Cliff. And from then on, he basically always won a fellowship. He did one postdoc with a Veni Fellowship, which is a Dutch competitive fellowship. And then he won another one, it's called VD. And then with that, he could start his own group in Leiden, again in the Netherlands. And now, as he said, he's in Barcelona with Ramon y Cajal, which is kind of a fellowship tenure track from the Spanish government. On a nice side, actually, he's actually active in outreach as well, and he's one of the founder of Quaternion Books, which is dedicated to the diffusion of scientific literacy. So they make books to diffuse science for the public, let's say. And he has worked on many various things, from quantum optics applied to astronomy, so instrumentation, and then on intermediate mass black holes and ultraluminous X-ray sources and radio pulsars, even conditions of exoplanets near pulsars. But the thing that he's most expert in, and it's basically he's the expert, is on the timing of X-ray. And so, for example, he worked on analysis of oscillation during type 1 bursts, but in particular, he is really focusing on accreting millisecond X-ray pulses and, for example, the recent discovery, the transitional ones. So today he's going to talk a little bit about this. And so, Alessandro, go ahead.
Okay, thank you, Yuri. Yes, thanks for this invitation. Today, I wanted to give you an overview of these fascinating objects, which are accreting neutron stars. I call this talk The Extreme Life of Accreting Neutron Stars, because neutron stars by themselves are already extreme objects because of their density. So you can do tests of strong gravity, you can do tests of nuclear physics, but they are also extreme from an astrophysical point of view, because you can do you can probe several astrophysical theories that involve plasma and involve magnetic fields when the neutron star is accreting, which means it's in a binary system. So the outline that I prepared for this talk is to focus on a specific problem, which is the problem of the spin of accreting neutron stars, which is related to both the nuclear physics that you can do with the interior of the neutron stars and with the role that gravitational waves play in these systems. Gravitational waves, when I say gravitational waves, I don't refer to the transient gravitational waves that we are used to read about, but I'm talking about the continuous gravitational wave trains that can be emitted by deformed neutron stars. And so far, there has been no detection of continuous gravitational waves by any of our laser antenna interferometers. Then the second part that I want to discuss with you is the role played by transitional millisecond pulsars, which are a relatively recently discovered class of accreting neutron stars, which behave in a very peculiar way. And then I want to give you some information about the puzzling case of one of these accreting neutron stars called SAX-J1808. And then I will try to wrap up to try to highlight the main points of for the future. The first thing that I want to say is about the spins, the neutron stars in low mass X-ray binaries and the open issues. First of all, when I say low mass X-ray binaries, I mean that the fact that there is a neutron star here that you can see in the center here, this tiny neutron star bound gravitationally with a low mass star, and that then the low mass star fills its rush lobe, transfer mass towards the neutron star, and then accretion occurs on the surface of the neutron star, and these are the so-called low mass X-ray binaries, because X-rays are produced in this process, and they come both from the disk and from the neutron star itself. And then you can see these X-rays, and those are called low mass X-ray binaries. There's also a version of the systems with black holes, and they're also called black hole low mass X-ray binaries. Now, the terminology that I'm using here, let me clarify a little bit about the terminology. From an astrophysical point of view, when you have a binary which contains a low mass star like our sun or less, and a high mass star, then after a certain period of time, of course, the high mass star could explode in a supernova, and then what you get is a neutron star. This neutron star might be a pulsar if it has a strong enough magnetic field. And so what we see with observations are radio pulsations. And there is no accretion ongoing in this phase, no accretion. Then after this phase, the low mass star can evolve, and the orbital separation can also change due to binary evolutionary processes. And at some point, the low mass star might fill the rush lobe and start to transfer the gas towards the neutron star. This forms an accretion disk. The accretion disk is made by plasma. This plasma interacts with the neutron star and might spin it up because of the transfer of angular momentum. Once the accretion process stops, in principle, according to what we know as the recycling scenario, the neutron star should turn, the neutron star should turn back on as a millisecond pulsar because of the spin-up process. So the rotation period now is in the millisecond range. And what is left is either the core remnants of the star, say a white dwarf or a semi-degenerate object, or there could be nothing left in the sense that the companion might be completely consumed. And that's how you form the so-called isolated millisecond radio pulsars, or the binary millisecond radio pulsars. And if you look at what is called the PP dot diagram that you see here on the bottom right, you know from radio observations that the young pulsars, the normal pulsars, spin in a range of the order of a second, between 0.1 and 10 seconds, let's say. Whereas you have a group here on the bottom left, which is made by very fast rotating neutron stars, which are called the millisecond pulsars. And that's the way in which these objects are formed through this process that I've just explained. Once the neutron stars become millisecond pulsars, another thing that observers have noticed is that their magnetic field, which in the beginning is of the order of 10 to the 12 Gauss or so let's say between 10 to the 10 and 10 to the 14 Gauss, has decayed during this process. And now these objects have a magnetic field of the order of 10 to the 8 Gauss. So this accretion process, this phase here in the number 3, produces both the spin up and possibly the magnetic field decay of the neutron star. Now, one thing which was discovered recently, which I will discuss in the second part of this talk, is that whereas in the beginning, in this recycling scenario, it was believed that this process of accretion and then turning into a millisecond pulsar was unidirectional. So it happens once, and then the binary continues to evolve as a radio millisecond pulsar here. It is now believed that there could be a back and forth process where the neutron star, sorry, the neutron star runs through different episodes of accretion. Then it stops. Sorry. Then it stops and then becomes a radio millisecond pulsar, and back again it transforms in a low mass X-ray binary accreting, and then back and forth. These are the so-called transitional millisecond pulsars that I will discuss in a few slides. Now, let's focus first on the low mass X-ray binary phase. In this phase, there is accretion. There's an accretion disk, I said, and the neutron star emits a large amount of X-rays. Sorry. These X-rays that come from both the neutron star and the accretion disk might be pulsed if there is a magnetosphere, but sometimes they are not, in the sense that we don't know why, but even if there is a neutron star here in the center, for some reason, if we look at the flux over time, we don't see pulsations, but we see a rather erratic behavior. Now, these accretion disks, as they form and evolve, are not always stable, in the sense that while the accretion process, the transfer of mass, let's say, from the companion star towards the neutron star is continuous. Sorry. Sorry, I was saying a bit of coffee.
Do you want to drink a little bit of water? Take 1 minute.
Yeah. 1 second.
Yeah, don't worry.
Okay, let's see if it works now.
You hear me?
So while we have
I have a question.
Yeah, I have a brief question. So
Yeah.
in this mass transition, say if the donadora donating mass star is not rotating, would that then spin down the neutron star?
No, it doesn't depend on the donor. So the stars are tidally locked because the systems are very close together. So the tidal interaction synchronizes them. So they are rotating at a certain speed, but of course, since they are far away from the neutron star, their specific angular momentum of the let's say of the gas of the donor contains very high angular momentum. So it doesn't matter where you are, even if you are very close to the neutron star, up to the point where you would be tidally disrupted, the specific angular momentum that comes from the donor is always going to be high, and so it's always going to spin up the neutron star.
Okay.
You can spin down the neutron star, but by a different process that I will explain in a few slides. Now, during this accretion process, the disk becomes extremely hot and emits X-rays. Some of these systems are so-called persistent systems. You always look at them and they have a relatively similar X-ray luminosity. But some of them are transients. And transients means that they go through 2 different phases. One where they emit a lot of X-rays, called the outburst, and here you can see an example of this. And sometimes where they emit almost no X-rays, let's say more than that, let's say orders of magnitude less X-rays, and that period is called quiescence. Now, the quiescent period is not very well studied because there are observational biases. Sorry again. There are observational biases that prevent us from studying this phase because it's very low luminosity and the X-ray telescopes can't collect enough photons. During the outburst, we see them very well. And for example, pulsations are studied when they are present during the outburst. Now, one thing to say is that the X-ray luminosity that you observe is usually proportional to the so-called mass accretion rate, or m dots, because of course, the more matter you throw towards the neutron star, the more luminous it will be, the disk and the material that lands on the surface of the neutron star. Now, during the transfer of angular momentum that I was explaining, if there is a magnetosphere, you will see that the disk is truncated in this inner region here, which I will show you in more detail in the next few slides. And the transfer of angular momentum happens here. So this material is rotating very fast, and then the neutron star starts accreting and is spun up. Now, there is a variety of low mass X-ray binaries, in the sense that there are low mass X-ray binaries that have a main sequence donor star, some that have semi-degenerate companions, and others that are ultra compact with orbital periods of less than 1 hour, where the companion is a degenerate object, say a white dwarf. And now there's a new category also called transitional, which have a main sequence companion star, and they switch back and forth between radio pulsars and low mass X-ray binary states. This is to say that there are this large variety, a large zoo of objects. Now, to give a little bit more quantitative explanation of what happens, this is the accretion disk, and as you see here, this is the magnetosphere. So you have a dipolar magnetic field from the neutron star, and this dipolar magnetic field interacts with the gas. So in the accretion disk, the gas in the accretion disk is spinning, and it's spinning with the Keplerian velocity, omega k. That, of course, is nothing strange. Then once the gas reaches this inner boundary here in yellow, this inner boundary is the region where the magnetic pressure, so the pressure, the energy density, if you want, of the magnetic field, greatly exceeds the gas pressure or the run pressure. Here, run pressure, say, is just proportional to the density times the velocity squared, and the gas pressure is just let's say, take the ideal gas pressure to get an idea. So there is this region where this happens, and this defines the so-called magnetospheric radius. It's called magnetospheric radius because here the magnetosphere dominates the accretion process. And so what happens here is that if you zoom in the neutron star, you will have that here the field lines interact with the gas. Here, this is the magnetospheric radius, and then the gas follows the magnetic field lines and lands on two poles, the magnetic poles, north and south magnetic pole, and hits the neutron star surface and releases energy, transforms rest mass energy into radiation. That's where the X-rays come from. If you look at the X-ray photons that are received by instrumentation, and you do, for example, a Fourier transform, you see a periodicity, and this periodicity is at the spin of the neutron star, because now the photons generated by the hotspot are modulated at the spin frequency of the neutron star. And here you see this very large peak. This is the peak that corresponds to the first accreting millisecond pulsar discovered, which spins at 401 hertz and was discovered in '98 by Wijnands and van der Klis. So you see a very strong signal. Now, the reason why, let's say, there is an interest in these objects is the following. And this is also to answer the question on how these objects spin down. as I said, there is this magnetospheric radius, which is called Rm. This magnetospheric radius depends on the magnetic dipole moment, so how strong the magnetic field is, and on the strength of the accretion rate. So if you throw much more matter, this m dot scales with inverse power 2/7. So the more you accrete, the smaller is the magnetospheric radius, which makes sense because if you put a lot of mass here, the ram pressure, the gas pressure are going to push this magnetospheric radius towards the neutron star. Whereas if you decrease or increase the magnetic field, either of the two, if you increase nu or decrease m dot, the magnetospheric radius will move towards a region outside, away from the neutron star. But then there is another point here, which is another radius of interest, let's say another length scale, which is the so-called corotation radius. The corotation radius is the point in the disk that rotates with the same angular velocity of the neutron star. So as I said, let's say each ring here in the disk is rotating with a certain Keplerian frequency, Keplerian velocity. There will be one ring that rotates at the same rate as the neutron star. So everything inside, suppose that let's say that this ring here that I'm drawing now is the corotation radius, is the ring that rotates at the same angular velocity of the neutron star. Then everything inside here will spin faster than the neutron star, and everything outside will spin at a slower rate than the neutron star. But then what happens if the corotation radius is inside the magnetosphere? So suppose that the corotation radius is here. Well, in this case, all this material here will be spinning at a slower rate than the neutron star. And when the magnetic field and the plasma interact, in principle, you should get a spin down because of the centrifugal barrier that forms. I will mention some research done in this area. I was very active on this when I was in Leiden, especially a few years ago. And there are many simulations that have been done recently, thanks to the advancement, let's say, of computational power available, that show that this process is extremely complicated. Okay, one thing that I want to discuss now is why, personally, why I'm so interested in this accreting neutron stars. Well, the reason is very simple. If you take the mass radius relationship of neutron stars, you know that this, let's say, the sequence of neutron stars that you can get are different according to the particular nuclear interaction that you use. Let me explain this briefly. When you look inside neutron stars, at the very center, the core of these objects is made by particles that, of course, that we are not completely sure which one they are. And the reason is because we don't know the details of the strong force, if you want, at those densities, because the density inside the neutron star reaches 10 to the 14, 10 to the 15 grams per cubic centimeter, which is completely out of reach for any Earth-based experiment. So by measuring the equation of state, so the mass and radius, we know the equation of state. And so we can put constraints on the strong interaction, for example. Now, because the strong force and gravity work together to give a certain radius for a neutron star given a certain mass, you know that at some point, if you keep spinning these neutron stars, you might break them because of the centrifugal force. And so, for example, if you look at this plot, if you look at this plot, this bottom region here is the region where the centrifugal force exceeds gravitation, the gravity that keeps the neutron star together, if the rotation of this object is 700 Hertz. So if we find a neutron star that spins at 700 Hertz, and we know one, then we know that this object of 700 Hertz cannot have, for example, a radius of 14 and a mass of, I don't know, 1.2, this would be excluded because this object would break apart. But we know that most neutron stars have a mass of at least 1.3, 1.4 solar masses. So this region is not particularly constraining. We don't know whether the equation of state is stiff, or so it's hard to compress the neutron star, or it's soft. But if in the future we would find, for example, a much faster spinning neutron star, say something at 1,200 Hertz, then the region that we would exclude is very large in this diagram, and so we would be placing constraints on the strong force by constraining the mass radius diagram. Now, there is one problem, though. Well, there are two problems. One of them is that most low mass X-ray binaries that contain a neutron star have an unknown spin frequency, or better, we don't know the rotational period of the neutron stars, accreting neutron stars in these objects. There's a tiny fraction of around 20% or so where we know the spin, whereas almost 80% have a completely unknown spin frequency. And that's a pity, of course, because we would very much like to find a very fast spinning neutron star, since the maximum that we found so far is for a radio pulsar at 716 Hertz. That's the fastest we know. But we do know that in low mass X-ray binaries, there are very fast neutron stars. Why we don't know them? It's because the pulsations are not present. And why the pulsations are not present, it's a complete mystery. Now, if we look at the distribution of spin frequencies of accreting neutron stars in low mass X-ray binaries, for which we know the spin frequency, there is something quite interesting that can be found. First of all, if you look here you have a histogram of the spin frequencies of 29 objects. These 29 objects are neutron stars where we know the spin frequency. As you see, there is a completely empty region here above about 650, 700 Hertz. In this case, this is 612 at 20 Hertz. That's the fastest accreting neutron star known. The fastest radio millisecond pulsar known is 716 Hertz. So it's not much faster than the accreting neutron star in low mass X-ray binaries. But what you see is that here there's nothing. And there is nothing, and there is this strange peak over here, which is actually statistically significant. And it's one might immediately ask, okay, but you said that if the neutron star spins very fast, the centrifugal force might disrupt the neutron star. So perhaps that's where the neutron stars stop, right? Perhaps here is the region where the centrifugal barrier wins over gravity. Well, then what you can do is very simple. You can calculate the maximum spin, this new max, as a function of the neutron star mass and neutron star radius. So you see that if you put any neutron star mass and radius for reasonable equation of states, you find that at least part of this region, let's say above 800-900 Hertz, let's say here, this region here should be populated. And to reconfirm this expectation, one can look, for example, at a recent paper from Reichmakers et al. That was published in February of this year, where the authors took the constraints that come from the nicer observations of a neutron star, gravitational wave mergers, and several other nuclear physics constraints. And then they determined that the neutron star radius for a 1.4 solar mass star should be about 12.3 kilometers, plus minus 0.8 or something like that. So if you plug these values in this equation, you find always that the spin frequency, the maximum spin frequency, is much larger than 720, 716 Hertz. So the lack of fast spinning neutron star is very perplexing. Actually, you expect neutron stars, even in this region here, in the sub-millisecond part. This is the sub-millisecond because we are at 1000 Hertz. Why this so is not...
A quick question there. how much is there a bias, an observational or an instrument bias for not detecting the large spin objects?
Observationally,
we have the instruments that could be.
Yeah.
Mhm.
The instrumentations are not biased up to 2000 hertz minimum. So this is not a problem of instrumentation, because in radio with the radio pulsars, you have a little bit of observational bias due to the presence of what is called the dispersion measure. So when the radio waves cross the galaxy, the signal at different frequencies disperses as it crosses the free electrons in the galaxy. Whereas in X-rays, you don't have this effect. So you don't need to search large parameter space. You just take your light curve, you do a Fourier transform, you should see a spike. And so this is not a problem of the instrumentation. It could be a problem of sensitivity in the sense that you can say, well, but if the pulsation is very weak, would you observe it? I will show you later that we have now searched many of these objects where a neutron star is accreting and we don't know the spin. And the upper limits that we can place are amazing, are very strong. It means that, for example, I remember we placed an upper limit on a neutron star of less than 0.1% in fractional amplitude, which means the flux varied less than 0.1% if there is an asymmetry on the surface. To give you an idea, if you take the sun, if you take a one day where the sun is very active, where there's a big sun spot, the variation we get in flux is about the same. It's about 0.1%. So imagine this neutron star, how incredibly uniform it has to be to not produce pulsations. So the bias is there in the sense that there are limitations of the instruments due to the collection of photons, but the data we have so far should have given us a detection in most cases, and we still don't see these pulsations.
Okay.
Now, sorry,
I have, sorry, I have a second question, which is part of this same idea. At what spin do you have this centrifugal barrier? So if I remember correctly, when I did a little bit of research on strange quark matter stars, and I remember that around 1 kilohertz, the centrifugal, or I forget the name you were using before, but if you spin much faster than that, then you would have a decretion disk rather than accretion disk. So could it be that you cannot spin them through this mechanism?
Yeah. It's this frequency here that you see, this new max, is basically that limits. That's obtained by equating the gravitational pull with let's say the push due to the nuclear force. In your case, when you say that you did the studies on strange quarks, we have to make a distinction, because strange quark matter, when you look at the strong interaction, in that case is attractive. Whereas in neutron stars where there are no free quarks, there is the repulsive barrier of nucleons. So if you switch off gravity in a neutron star, which is not a quark star or a strange star, the neutron star would explode. Whereas in the case of strange quark stars, they are self-bound. So if you turn off gravity, they still keep they still stay together. So in the case of strange quarks, this limit might be different, because you cannot do this. You cannot equate the gravitational force with the nuclear forces, but the principle is the same. In that case, you need to have indeed, strange stars can spin faster than normal neutron stars because of this attractive part of the strong interaction.
Right.
Now,
okay, thank you.
Yeah, if we look at this distribution, and you do a statistical study, I'll go a bit quickly on this because I want to show you some results. But just to say that in this case, if you do a kernel density estimation, what you see is that this distribution is bimodal, basically. Now, there are very few pulsars, so be aware of the fact that the statistical significance of what I'm saying and what I will tell you now is not astounding, because we're working with a very small sample, but it's still significant. So all the statistical tests show that this distribution is indeed bimodal. But another thing that I did was, we did a few years ago, was to take this distribution and try to fit it, what was called the Gaussian mixture model. Gaussian, basically, the long story short is that we tried to see whether this distribution was better described by one or by two Gaussians, or maybe three Gaussians. And what we found was that two Gaussians was the best description of this object. Now, what you have here is this P1, P2. Basically, what you find is that there is a cutoff. There's this line here that represents a cutoff at 540 hertz that divides the two populations. So there is a relatively slow spinning subpopulation and a relatively fast spinning population. And there is this peak here that you see, that you see here on the right, this peak here. And this peak is very intriguing because it has appeared almost immediately in the early 2000, no, in the late 2000s, I should say, and then in the last decade has kept growing and is still there. So it seems to be real. Okay, the reason why I mentioned this is because maybe there is some mechanism that prevents this object to spin faster than this limit that we see here. And one possibility, well, another intriguing thing is that if you take this cutoff at 540 that I found from the distribution, and then you look at the surface temperature of neutron stars, what you see is that with circles, you have a measured temperature in a million kelvins. And when you see an X cross, I should say, a cross, these are non-detections. So it means that the temperature is lower than this value. And the hottest, well, or at least almost all the ones that we have a detection for are close or above this cutoff limits. And I mentioned the temperature because the temperature might be related to continuous gravitational wave production mechanisms that slow down the neutron star. So the idea that there was at some point is that you have different mechanisms, but let me focus on this one, the so-called crustal mountains. When you throw matter on the surface of the neutron star, basically you compress a little bit locally the crust, and you trigger some pycnonuclear reactions deep in the crust. So here you have the ocean of the neutron star, and this is the crust of the neutron star. And so you change the composition, you change the nuclei that compose this neutron star, and you get this asymmetry, and this asymmetry gives you a mass quadrupole, and the mass quadrupole, this Q22, basically generates a train of continuous gravitational waves, and these gravitational waves slow down the neutron star. And so maybe that's a brake mechanism that prevents these objects from spinning too fast. Now, given that we have this hypothesis, let's look at one system, which is this pulsar J1023 plus 0038, which happens to be one of these transitional millisecond pulsars. I mentioned this object because there is a possibility that this object is indeed emitting this continuous gravitational wave train, although there are many other possibilities, but I find this the most compelling case we have found so far. First of all, let me say very briefly, what are transitional millisecond pulsars? As I mentioned, this object is a very special one. It's a millisecond pulsar binary. This was known since 2003, I think. It's a 1.7 millisecond pulsar. It's a radio pulsar, at least it was in 2007, the moment of its discovery. So it was spinning, here is the neutron star, and there was a low mass star, and it was not accretion. There was no accretion ongoing. Now, these radio pulsars in principle, the idea behind the radio pulsar emission is that a radio beam is generated from the free electrons that are extracted from the crust or that are part of the, or are close to the surface of the neutron star. When the light cylinder is empty, is not filled with a disk, which means, what is the light cylinder? I mean, the light cylinder, since the magnetic field of the neutron star is a dipole or close to a dipole, even if it's, you know, ideally is a dipole, let's say, you have that some magnetic field lines rotate and then close to the other pole, and they rotate faster than this. They need to rotate faster than the speed of light when they reach this point. So they open and then they close at infinity. And this is the so-called light cylinder. And this light cylinder needs to be relatively empty. This neutron star was showing a spin down as all millisecond pulsars, radio pulsars, and the spin down was nothing special. It was this value here, minus 2.4 10 to the minus 15. But then in
Alejandro?
2000, yes?
Yeah, just a very naive question. Why could it be possible not to have a disk in this kind of
So
system?
if there is a disk here, so let's say that the radio pulsar, the radio emission in millisecond pulsars or in pulsars in general is given by a very delicate balance of physical parameters. In other words, the electrons need to emit coherently as they move and they're accelerated along the magnetic field. So if the magnetic field is filled with plasma from the accretion disk, for example, then these electrons are destroyed and you can't have radio emission. At least for the radio beam, you can't have a coherent emission process. The radio beam is a coherent emission, so you need to have a very delicate balance that occurs in the light cylinder. If you fill it with plasma, you destroy basically the coherence of the emission. You can still have incoherent emission, thermal, synchrotron, whatever, but not coherent radio emission.
Okay, thank you.
Now, this object was discovered in 2007, but then archival observations from the Sloan Digital Skyfer survey in 2001 showed a spectrum that corresponded to a disk plus a companion star. So this is the spectrum of the G5 dwarf star companion here. And this is the spectrum, sorry, and this one, this dotted line, is the spectrum of a disk that you need to add to have the observed continuum. This is the observed continuum from the archival data. Furthermore, other observations in optical showed the presence of an H-alpha emission with this typical double horn. And this double horn is due to the rotation in the accretion disk, so the Doppler red and blue shift. And so there was a disk in 2000, 2001. So this object transformed from a low mass X-ray binary into a radio millisecond pulsar sometime between 2001 and 2007. And this was the first to show the transitions between radio pulsar and accreting states. Well, this one we don't need. So this is an observation in radio. It's quite complicated, but all I want to show you is that you have the radio observations of this object, this pulsar J1023. When you see a circle, it means a detection at a certain orbital phase. And on the x-axis, you have time. And then in the bottom panel here, you have the gamma rays from the Fermi-Lat detector. And basically, sometimes you see crosses here, for example, large bunch of crosses. Those are non-detection, but that's normal because these objects have some gas from evaporation of the companion star that blocks the radio beam. So this is totally normal. But at some point around this time, in July 2013, the detections in radio disappear and you have only crosses here. The radio pulsations disappeared, and you see at the same time that the gamma rays increases all of a sudden by a factor of a few. And this is when the radio pulsar transformed into low mass X-ray binary. So here there was a radio millisecond pulsar, and here there is a low mass X-ray binary. There is this skew here because the X-ray luminosity that we observed, it was of the order of 10 to the 33 ergs per second, which is not the one that you see during outbursts, but it's typical of quiescent low mass X-ray binaries. This gamma ray emission, however, was very puzzling because we don't know low mass X-ray binaries. At the time, we didn't know any or even any candidate with gamma ray emission. But this became very bright. Well, let me skip a few things. So this is the timeline of this object. So the archival observations showed that between 99 and 2001, sorry, in 2000, it was a radio millisecond pulsar, then became a low mass X-ray binary in red. Then it turned into, again, into a radio millisecond pulsar. And then in 2013, again, became a low mass X-ray binary, and it's still a low mass X-ray binary. Now, this is interesting because the accretion process occurs in a very funny way. If you look at the X-ray light curve during the low mass X-ray binary phase, you see this subluminous state is called. As I was mentioning, it's of the order of 10 to the 33 ergs per second, so typical of quiescent low mass X-ray binaries. People usually call it subluminous state because we are not sure it's really the quiescent low mass X-ray binary state because we are not sure these objects are the same thing. What we see is this flickering. So you see this part here in green, which highlights this bottom region here, where the flux is very low, and it reaches about 10 to the 32 ergs per second. Then there is a more stable part here in gray, which is about 10 to the 33 ergs per second. And then there are flares that reach up to 10 to the 34 ergs per second. And if you look at the X-rays, you see X-ray pulsations. Here is the X-ray light curve, folded light curve, as a function of the rotational phase of the neutron star. And you see that there are X-ray pulsations. So we thought that this is the first accretion-powered quiescent low mass X-ray binary. I say the first because all accreting millisecond X-ray pulsars known so far have shown pulsations in outburst and not in quiescence because of poor low number of photons, let's say. This one instead, which is very close, I should say, it's only 1 kiloparsecs away, might be the first quiescent low mass X-ray binaries, and then maybe we are seeing accretion during this quiescent state. However, there is a little problem, as I will show you. The first thing is that if you split up this light curve into these three phases that I've shown you, three different luminosities, you see the pulsations only during this gray stable 10 to the 33 ergs per second state. So these pulsations that you see here, they come from this state here. There are no pulsations in this red and green area with pulsed fractions of less than 2%. So for some reason, the accretion must be intermittent or something like that. But the point is, the reason why I mentioned this object is that if you calculate the luminosity, because we know the distance very well, and how much mass has been accreted so far up to today, the delta M, the total mass accreted, is of the order of 10 to the 21, 22 grams. And this mass has been thrown on the magnetic pole of this neutron star. And so, as I was mentioning, if you take the amount of accreted matter to be of the order of 10 to the 21, 10 to the 22, you can build one of these so-called crustal mountains, this density asymmetry in the crust, and maybe you can hope for the emission and creation of a continuous train of gravitational waves. So you can create a mass quadrupole. If we look at the spin of this neutron star during the low mass X-ray binary phase, what we see is that the spin down during the accretion phase is slightly larger. It's 1.25 times the spin down that you see during the radio phase. So why there is this excess of 0.25 here? Where does it come from? So one idea was to say, well, if the spin down is as this 0.25 excess with respect to the radio, maybe we can ascribe it to the gravitational waves emitted by a potential crustal mountain, presence of a potential crustal mountain. And so you can calculate this mass quadrupole, plug everything in, and see whether things make sense. And what we found is that they seem to be consistent with this idea that if you try to build a crustal mountain on these objects, you can create a mass quadrupole that is compatible with the magnitude of the extra spin down, that 0.25 extra spin down that you observe. And the funny thing now, without going through the calculations because they're not particularly enlightening, you can see that if you look at this crustal mountain that you have created, this asymmetry that you create here, this one dissipates on on a thermal time scale. And once this dissipates, basically the crust of the neutron star is not uniform in the sense that it's not the same composition, but is stratified like an onion. There's no more mass quadrupole. Okay, so there are observational tests that one can do. For example, you can observe the radio pulsar when it turns back into a radio pulsar, and you should gradually see the spin moving back to the new dot radio. So lose this excess 0.25 extra on the thermal time scale, because you need to dissipate this mountain. Or another thing which is a bit more difficult is to observe a gradual increase in the accretion on this new dot accretion. So this excess of 25 should increase to 0.3, 0.4, whatever during time, because you increase the mass quadrupole. But the observations are exceedingly difficult to do. The funny thing is, or interesting I should say, is that if you calculate the signal of this object, this bar here corresponds to the possible detectable signal in an advanced LIGO with 33 months integration. So it's potentially observable if true. Now, the spin down has many other possible explanations. One is the propeller. As one of you was asking, is it possible to spin down these objects? Yes, it's possible. If the magnetospheric radius is larger than a bit more than the co-rotation radius, let me skip y is 1.3 for now, but let's say it's larger than the co-rotation radius, then the magnetic field lines open up, they inflate, open up, and you have a conical wind and an ejection of material from the innermost regions of the neutron star. And basically the centrifugal barrier, it's a bit like the merry-go-round. I mean, if you try to jump on something rotating very fast and you don't have enough angular momentum, you're going to be ejected by the centrifugal barrier. So this is what happens. The gas goes in and then feels the magnetic pressure, and the rotation bomb kicks the gas away. And you transfer angular momentum from the magnetic field, so the neutron star, to the disk. Well, maybe we can skip this part, but there is also an interesting observation, which is this. If you look at the radio emission, not the pulsation, I'm talking about VLA observation, very large array observations, continuum, radio continuum, you can see that there is a very, very strong anti-correlated light curve. So you see here, this is the radio, and this is the X-ray, this is the flickering you were seeing before, and they are extremely well anti-correlated. And this adds further support to the theory of ejection. So ejection might stop the accretion and increase the outflow, which increases the radio emission and decreases the X-ray luminosity. But then there was this point, which is important, which is that a few years ago, there was an optical pulsation detected in pulsar J1023 during the low mass X-ray binary states. And optical pulsations are not expected in accretion in low mass X-ray binaries. So the question became, okay, where does this optical pulsation come from? Usually they come from synchrotron emission in radio pulsars, not in accreting systems. The amplitude of the pulsation was low, but was very significant. You can see it here. So is this pulsed magnetospheric synchrotron emission? Yes or no, we don't know. But if it is, how can the neutron star have the emission of a typical isolated or binary non-accreting system and an accreting one? Another thing we found was it's really recent, we just submitted this paper. We found also potentially UV pulsations. So this is a potentially UV detection of pulsations in pulsar J1023, which reinforces the idea that this is synchrotron emission. And so this is not a typical accretion signature. On the opposite, on the contrary, is a non-accreting signature. Oh, and now let's talk about this other object, SEX-J1808, very quickly, because I think I ran out of time. But just to show you one thing, this system is the very first accreting millisecond pulsar discovered. Sorry, is the very first accreting millisecond pulsar discovered. This is accreting for sure, because we see an outburst. We see an outburst. The light curve is of the order, and this is time. And the flux here is of the order of 10 to the 36 ergs per second. There is no way to do this if you're not accreting. So this is accreting 100%. If you look at the system, it was reported a few months ago that this system shows during accretion optical UV pulsations. So this is the X-ray light curve, and there were observations here and here. This is from the Telescope Nazionale Galileo. You see are the pulsations here from the rays. See the pulsation here from optical. So again, this is probably you're confused, but I'm confused too, in the sense that the X-ray pulsations are present are due to accretion, but there's also optical emission that cannot be due to accretion. Well, this object is strange because in quiescence, it's spinning down, and this is, you can see here, this trend here is the spin down during the last 13 years. It's spinning down. It was thought to have an active radio pulsar during quiescence, but this radio pulsar was never detected. We tried to observe SEX-J1808 using the Green Bank radio telescope. We placed quite strong upper limits of 30 microjansky at 2 gigahertz, but there are no radio pulsations during quiescence. But during the outburst, we see optical pulsation, which is puzzling, because again, optical pulsations should be shown when the system is a radio pulsar, or at least if not a radio pulsar, where it's not accreting. So perhaps we thought during quiescence it's accreting, but it's although in quiescence, you see that all of these 18 millisecond pulses, including SEX-J1808, show H-alpha emission line. And again, in this case, if you see the spectrum here, this is the H-alpha emission line in SEX-J1808. And this H-alpha emission line in quiescence is not seen in the other system, in the transition second pulsar 1023. So what's going on here? The transition second pulsar, an extra state that does not appear in canonical accreting millisecond X-ray pulsars, but even in that case, the accreting millisecond X-ray pulsars like SEX-J1808 appear weird because they show signatures which should not correspond to the accretion phase, and still they see this, have these optical pulsations which are totally not expected. Well, so just to conclude, I was showing you that there's accreting millisecond pulsars in low mass X-ray binaries might be split into two subpopulations, one at high spin frequency, one at. If the high spin frequency population cannot advance above a certain spin frequency because of gravitational waves, then we might have a possible observational transitional pulse of J1023. However, the presence of optical and UV pulsations during this, let's call it subluminous state, are really weird, because it might mean that it doesn't accrete. But in accreting systems, canonical accreting millisecond pulsars like this optical UV pulsations are observed during the accretion phase. And so this is something not created by accretion theory. So something weird and unknown is going on. So maybe it's still possible that these objects are behaving all in the same way. And maybe there is a ability to test this theory in the upcoming future. I am done. So I don't know if I am over time, and I apologize if I spoke too much, but I don't know if you have further questions.
Does someone have questions?
I have a question.
Yeah.
So I didn't quite understand in the interesting pulsar that was sometimes radio and sometimes mass X-ray binary. So what's happening to the system? So that
well, you're not the only one that hasn't understood it, because nobody knows why this happens. So what we see are these sudden transitions, I should say, between radio and low mass X-ray binary. And the reason why this happens is not known. There are some hypotheses, let's say more speculative than the real theories. One possibility is that the neutron star, the pulsar, beside emitting radio waves, optical pulsations, and so on, emits also pulsar winds. And perhaps here, you see in the radio phase, perhaps this pulsar wind tries to overcome if it can overcome the pressure of let's say the mass transfer, perhaps it can prevent the gas from flowing inside the Roche lobe of the neutron star. But then for some reason, this wind turns off, and the accretion flow at this point can penetrate inside the Roche lobe, and you can create an accretion disk here. And then you get this phase, the low mass X-ray binary phase.
Okay.
But also in this case, why then this stops and goes back to the radio pulsar state is completely unclear.
Okay. Okay. Thanks.
Does someone else have questions?
Yes, I do have one more. So when you take these radius for the magnetic pressure, you assume that the magnetic field is a dipole. So how good is that approximation? I mean, I remember reading about NICER and measuring some of these pulsars, and they didn't really seem to be that much of a dipole, right?
You are right, and it's a terrible approximation. You're completely right. The reason is that, there is one thing to say. Close to the neutron star, they should be, at least in the accretion phase, but also in the radio millisecond pulsar phase, you should expect something relatively close to a dipole. Then, of course, as the magnetic field interacts with the plasma, it changes shape, right? You cannot have a dipole, pure dipole, if you have plasma mixed in it. The rotation of the accretion disk inflates the neutron star magnetic field. From radio, we know that from measurements of timing, we know that none of the radio pulsars has really a pure dipole. But let's say that it's close enough because the shape of the pulsations that you see are relatively sinusoidal. So it means you're probably seeing one or two poles. It's hard to believe that you have a much more complicated shape. So I doubt that you have the quadrupolar or octupolar components to be the strongest. So let's say in brief, if you take the magnetic field and you decompose it in its dipole, quadrupole, octupole components and so on, the dipole is going to be the strongest one close to the neutron star. So in that sense, is a good approximation of a dipole. But overall, the shape of the magnetic field is not dipolar at all, at least on large scales.
Thanks.
And someone else? It looks like no one else has questions. So I would like to thank you for the talk. It was a really nice talk.
Wait a sec. If I can ask him a question.
Who?
If I can ask a question.
Yuri.
Oh,
Yuri.
yeah, of course.
Sorry, it's Yuri. No, it was it was about the optical oscillations. So at the beginning there were the optical oscillation in the transitional. So people thought, it's not accreting, so it's something
Right.
weirder. And then they found them in Sachs J1808, and then they said, then it's okay, it is accreting.
Yes.
Or it might be accreting. Are they similar, the two oscillation in the two systems? Or
Yes, they're quite similar both in amplitude and characteristics. And so indeed, you are right. And the Sachs J1808, it must be accreting. There's no way it's not accreting, because accretion is very efficient in transforming in creating X-rays. And you can't get the luminosity that high with the synchrotron or whatever other process. So this must be accreting. And the optical UV are very similar in both cases. Okay. So you're right. The question, I in the beginning believed 1023 was accreting. Then I saw the optical, I thought, well, maybe I was wrong. Now I saw this new result, I think I was right, but I'm not sure. So.
But the last thing is there any idea where they come from?
Any?
Because they are if there is any idea where they come from, because they are at the spin of the star, right?
They are very similar to the optical UV pulsation that you see in radio millisecond pulsars. So this has to be magnetospheric and synchrotron emission, probably. It's possible, in my opinion, maybe both things go on at the same time. Maybe you have synchrotron emission far, close to the light cylinder, and accretion very close to the neutron star. Also, you never see coherent radio emission during this phase, which tells me that there is plasma in the light cylinder, because optical UV and X-rays are not coherent processes. These are thermal or non-thermal, but are not coherent, whereas a radio has to be coherent. And the only coherent one is gone. And perhaps these two incoherent mechanisms, synchrotron and thermal or Compton emission from the surface of the neutron star, are not incompatible. The theory is quite poor, so there's space for improvement for sure.
But still, the accretion has to be channeled because you see the X-rays.
It has to be channeled, and that's pretty convincing from what we see. Now, I skipped one part, but these systems that they are all, I mean, I would be shocked if turns out they're not accreting. I cannot think of any other, I mean, this is fundamental basic principles. First principles, I would say, because it's accretion that transforms the rest mass to rest mass energy into radiation. And that accretion is very efficient. You have 10-20% efficiency. With synchrotron emission, forget about it. This is not going to work if you want to explain the X-rays in that way.
Okay, I am more confused now, but I was.
Yes, everyone is, I think.
All right. Okay. Thank you.
Thank you, for having me. It was a big pleasure.
Alessandro,
Yeah,
thank you very much.